Hi there. So we're live coding today, and the topic is extending the studio development tools to do a better job of showing us what happens with compilation events in RaptorJIT. So in other words, when you write a Lua program and you run it and it gets JIT compiled, in a particular way, and it runs and you're profiling it and everything, then when you want to come back and look at the program and see why was it compiled the way that it did, and particularly if there was any code that was not compiled at all, that ran interpreted, why did that happen? And this is a bit of a needle in a haystack problem, in the sense that the JIT wakes up very often and compiles a bunch of code, and you need to make sense of which events were actually interesting, which events were significant. So if you see code running if you see the profiler saying that some code is running interpreted, then that's significant because the profiler saw it, so it's obviously impacting performance. And then you need to find a way to kind of work backwards and see how it ended up in that state. Why didn't it compile? So that's what we're going to look at today, and we're going to hop straight in. And I made two kind of sub parts to this. One is to show to reliably show the. I'll need to illustrate this with an example. We might do that first, and then we'll come back to what the to-do list is. Because this is something I started working on a little bit, and now we're just going to kind of try and take the next steps, wrap it up if we're lucky. So here we have a Smalltalk UI image. I'm going to open the Studio Inspector. And now we have the basic Studio UI. And we're going to write a small example program, and as we go along, we will profile this and diagnose it, and try to make sure that the tooling supports this and makes everything kind of easy. So to start with, we're gonna, what are we gonna do? We're gonna make a almost but not quite completely trivial program. We're gonna tell Nix we want to run some RaptorJIT code, and the code will be a loop, runs, let's say, 1 billion times, 100 million times it should do, to get us some profiler data. And the loop is going to have two branches. If the loop index is even, then we're going to say x equals x plus 1. Whereas if the loop index is odd, what are we going to say? We're going to say x equals x plus 2. So the compiler is going to, wait, well, yeah, this example will do for getting us started. So the compiler is going to compile this loop, and it's going to end up with one of these branches as the so-called root trace, and the other branch as a so-called side trace, because every time control flow diverges, you end up getting a separate block of machine code. You get one block of machine code to represent each kind of linear flow of control. So let's compile this, see what happens. This is just to give us something to look at, so that I can blank it up. I had some kind of error there. We still haven't made the error reportage decent. Let's just stare at it for a moment. I left off the do. Okay, fine. Error again. And again, we haven't got decent error reported yet. I'm missing one end. And we'll run that. We still got an error. One day we need to put in proper error messages. We don't have to be fucking around. Now I'm just going to quickly see. Looks actually embarrassing. What about if we open another inspector? We do a simple program just to start with. Wrong. Such a simple program as that run, as we expect. Yes, that runs and gives. Then why? Ah, silly me. It's probably because we don't have X defined anywhere. We can't add anything to X when it's undefined. Wow, we really need to fix those error messages. We don't have to do so much guesswork. But anyway, that's not the fish that we're frying today. Okay, that's a bit better. So now we get one profiler dataset, 351 samples, again once per millisecond. Everything ran in machine code. Error, probably something I've been... Okay, so I've been hacking on this code. Looks like I broke something. I've been refactoring and kind of redoing a little bit the code for handling trace events in the log. So here, what was happening? We tried to call GC trace with traces. Don't have that method. The trace stop event. Asking to do GC traces not working. So not have it. That's something that I deleted and shouldn't have. I've been adding and deleting and moving that around. I might have moved this from a subclass into a parent class. I lost track of it or something. GC trace with. Okay, let's grab that. Grab that method. Pop back in. Try that again. I've obviously been breaking some things, but that's fine. Have to figure out what they are, fix them. So what's happening here is that decoding the JIT log, have a trace stop event that represents a successful JIT compilation. And decode the trace stop. It tries to decode a C type called GC trace at a particular address. That address, nil. Something is a bit fishy. Try to get the traces. We have a trace stop event. It doesn't have GC trace. Okay, so I think I have an idea of what I might have mucked up there. Let's go into bear with me while I just get the basic stuff working again. So we're supposed to pull out the GC trace. I think then I move that up into a... We have two kinds of trace events in the log. We have trace aborts and we have trace stops. Trace stop includes a successful trace of machine code that we want to reference and is now missing, whereas a trace event has an error message instead. And what we have is this superclass trace event method that pulls the JIT state. It doesn't pull the error reason because that's only for aborts, and doesn't pull the trace because that's only for success. So then in the abort we have a subclass method that does the superclass method and then pulls the error message, and we're supposed to have something similar in the trace stop, but we don't. Okay, so again we'll look at where we mucked that up. We'll go into the code changes list, see what silly thing I did there. Not that method. What are we looking for? It's from the flashback. That's what's missing. Is pulling out the address of the trace in memory. We didn't grab that. So when it tries to decode the event, it doesn't know where in the heap snapshot to look for what it needs. So fix that. We will fix that in. Yeah. Copy into safety that line of code that we want, and we want a method that looks very much like this. And that second line is going to be this. So when we decode an entry from the JIT log, the audit log, that represents the trace stop, we're going to get all the usual trace data out of it, and we're also going to get a field called GC trace, which is going to be the address in the heap of the machine code that was generated. So let's see if that is any better. That's better. We have this really nasty name there. That's just a file name. That's an artifact of the way it was built. I need to another time shorten that to something more punchy. Anyway, we got two traces here, and that's what we said that we were expecting, right? We should have one trace representing this, the if then, and another trace representing the if else. And I couldn't guess offhand which will be which either, because it's just going to depend. The first time the JIT makes a compilation attempt, it'll pick that, the trace number 1, the root trace, and then it'll pick the other one to be the side trace. There's actually something interesting here for tracing JIT aficionado, that the root trace is spending more time is being spent in the root trace according to the profiler than in the side trace, but it's kind of actually indirectly, I'm digressing, it's kind of indirectly actually the side trace that's spending the most time, because if we look inside this this first one, we'll have this looping part that should run quite efficiently. But every time we exit out to the side one and rejoin, we're going to have to come back in at the top and do the stack loads and stuff. Anyway, it's a long story, but the profile. Anyway, the other thing to see here is, in addition to this profiler-driven view, we've also got this list of events in the JIT. We have two trace stop events. The file names are really quite ugly. It's a bit distracting, but I just apologize for that. So we had a trace stop event. Okay, never mind. Where trace stop event where we had a successful JIT compilation on line 4, and then we had another one with a successful JIT compilation on line 5. But if we make the example a little bit more interesting and introduce some failures in the JIT, then it can start to bring us in the direction of what we want to do. So now suppose on this branch, instead of just running that, if we ran that in such a way that the JIT won't handle it, so if we would say function, like that, suppose we wrap it in a function like that. Now the thing is that the JIT will not JIT compile the creation of a function closure. So this should be kind of semantically equivalent, more or less, but the JIT should not be able to do that. So if the JIT tries to compile this else branch, it should fail with an abort, and if that happens repeatedly, then it should end up compiling some code that goes off into the interpreter to run this instead. And that gets us closer to what we actually want to be dealing with right now. So let's see if that really happens when we run this. Yeah. So let's stop in the profiler just for context. Now we got a lot more profiler samples. And now we got this second trace is running, going into the interpreter. It's spending a lot of time, and whereas before we had 100% machine code time, now we've got like 62% in the virtual machine, which basically means interpreting bytecodes usually, and 32% time in the garbage collector there. So this represents a kind of like a catastrophically bad change we made to the program. So over here we made one path of control, something that can't be JIT compiled, and this meant that we ended up with a trace that is spent a lot of time, got a lot of profiler samples, and it went out into the interpreter, and then it got billed for all of the time that was spent in the interpreter. So this is actually basically the use case I'm interested in now. If you're running a program and it goes really slow, and you say, what the hell's going on? You should be able to trace it through and see, okay, you know, we're spending very little time running in compiled machine code. It's mostly in the VM and the GC, so that's the real problem. And then you should be able to trace that back to understand, you know, what was the real issue here, and that's what's missing, right? So now we can see trace number 2. You can see here that trace number 2 is spending its time going into the interpreter and spending a lot of time there. If I make that a little bigger, we can also see the line of code that's on. So we can see that line 9 was the problem, but what is the problem with line 9? We don't want to guess, because there are a lot of different things that can happen to prevent JIT compilation, and we don't have an encyclopedic knowledge of this as kind of casual developers. So we want more verbose information, and that's where the JIT events log comes in. So we get an abort there. I really must shorten those file names so it's not so hard. So we got an abort, aborted after 3 bytecodes. Then we got also a success. That success probably represents the then branch, and the abort the else branch. And then we got another abort, and another abort, and another abort, and another abort, and this abort was marked as final. This means that the JIT has tried that specific starting point for compilation enough times that it says this is not something that we can compile, and it gives up. And once you get a final abort, that's followed by a success of a 0 bytecode trace. What that actually is just an empty trace that exists only for the purpose of transitioning into the interpreter. So that's what this trace number 2 that we have is over here. Trace number 2 is it's just an empty bit of machine code that does a transition into the interpreter. You know, it spends a lot of time there. So what we really want to do here, once we see this, we want to at our fingertips know that, okay, then that these aborts are the reason that these are the interesting things we should be looking at. And when we click on one of these, yeah, we want to see the error reason. It was a not yet implemented bytecode. We can see the bytecodes. We can see it was a fnew, which is a new function closure. So once we find the abort in the log like that, change the size of it. So once we find the abort, we actually have a lot of really good information, right? We can see where did the trace start, where did it end, how many bytecodes did it trace, what was the reason, and for each compilation attempt, was this a final kind of failure? In the case of that one, yes, that was the final one. This is good information, and here we actually can see everything that we need. It's telling us that on line 9 we have a bytecode that's not yet implemented by the JIT compiler, that the JIT compiler can't compile. We hop over the bytecodes and we can see that that's an F new, which we can look up and see that that's a new function closure. So it's telling us pretty clearly, once we know how to look, that this new function closure we're creating here is the reason that the code could not compile, which is the reason that it branched into the interpreter, which is the reason that it's running slowly, which is the reason that it took about 10 times as long, something like, than the previous run. So that's great. Well, that's pretty great anyway. It's good enough for me. That's what I want to have, but I want to have this in bigger programs. So if this was a bigger program like Snap, we'd have hundreds or thousands of entries in this log, and it would be very confusing trying to scroll through and see which aborts. If you have 1,000 aborts, then which ones are relevant in a particular instance. And most of them are going to be completely irrelevant. Most of them are not worth your time to even look at. Some of them are going to be really crucial. So how do you piece that together? And that brings us back to our little to-do list. So first is a small thing. I want to make sure that when we print those lists of aborts, that you always see the starting position, and there's a special case that's not working there that we see here. So it says starting from question mark going to question mark, and the problem here is that trace doesn't contain any bytecodes. This is one of these funny little traces that only exists to enter the interpreter, and just the way in the GUI, the way it implements this start line to end line thing is to look at the location of the first and the last bytecodes, and that doesn't work if there's no bytecodes. So we need to I want to make this print a good starting line there by looking not at the bytecode but at somewhere else. The other thing that's a bit more significant is I'd like to be able to index from a trace that we see in the profiler back into that list to get the aborts. So specifically what I want to do is I want to go into this profile list, I want to go down, I want to say, hey, this was a trace that I don't like how this is performing, and I want to click on that, and up here I want to have a new tab which is going to say JIT, and in the JIT tab it's going to list all the entries from this event log that are directly relevant to that trace. So when I want to know why did this run in the interpreter, I just want to have a little tab here, JIT, and I'll click on that, and I want to see a very, very short list of the specific JIT actions that led to this being interpreted. And in our case, that would be half a dozen aborts there or something like that. So let's implement this, and it's interesting always with doing Studio and RaptorJIT, because RaptorJIT is logging raw C structs straight out of memory onto a file, and these are only partial snapshots. So it's not snapshotting the whole heap, right? That's going to be gigabytes and gigabytes, and we only want to really snapshot kilobytes or hundreds of bytes at a time, because we want to keep the total log file down. So it's possible, I think probable, that I don't have all the information I would like in the log at this point, but I think we also probably have enough. So if we just look at the simple problem first, we have here a trace stop, successful compilation, but it's with 0 bytecodes, so it doesn't print any meaningful name for the starting and ending positions. So I want to just look at fixing that right now. And so here we have that trace stop object in the Smalltalk object inspector, in a kind of a raw view there. So see what. See. The first thing I want to do is what? The trace stop event, but I guess it could be an abort as well. Generally speaking, anytime we have a trace event with 0 bytecodes, then we want to be able to establish where that attempt started, regardless of whether it was successful or not. So going back to our little object hierarchy, have trace event up there. There's the abort and there's the stop. So we want a common method for those, which is going to be here. And we have already got this method start source line way up there. They should be there, but not like that. We have a method start source line, and if there's no bytecodes, it prints a question mark. Otherwise, it prints the location of the first bytecode. So this works fine if there's at least one bytecode, and it doesn't work if there's no bytecode. So basically, this is what we want to fix right now. We want to replace these two cases with one thing that always works. And to do that, we're going to need to see what we've got to work with. So we're going to have to open this JIT state object up, see what's inside. So let's do that. Okay, so here's a JIT state. And so our JIT state is the name of a Smalltalk object that represents a JIT state. That's the internal data structure that the JIT has when it's doing compilation. If we click on that, we can actually get the DWARF level view. So this is a bit of a kind of an insight into the way that Studio looks at things. So again, RaptorJIT, the virtual machine, is logging raw C structures with no kind of formatting of any kind. It's just straight out of memory, copied into a file. And then the GUI here is decoding those using DWARF debug information. It's doing the same thing that GDB does in order to make sense of things. So this is good and bad, right? So we've got anything that you could do in a kind of a GDB macro, basically, you can do here, because you have the raw data. But the bad thing is that you need to go down to that kind of a low level. And that's where you're operating. So we need to kind of look here. We can also look at the C header file to see the definition. But basically, this is the information that we have about the state of the JIT at the time a trace, success or failure happened. And what we want to do is somehow get from this. For our first thing, we want to get the starting location of where the compilation attempt, where it begins. That's going to let us replace that question mark with a proper source line. And then the other thing is we're going to want to be able to match these up. We're going to be able to want to say, hey, was this JIT event relevant to a specific trace, for example, that ended up in the interpreter? So first things first, we're going to look through here, and we're going to try to find a way to figure out what is the starting line. So this represents the internal state of the JIT when it has either successfully or unsuccessfully attempted to compile some code, and we want to look in here and see where did that compilation attempt start, on which source code line did it start, without referring to bytecodes, because we don't always have any bytecodes recorded. So let's scroll a little bit. So PT is promising. PT is a prototype, C-type GC proto, and a prototype. A prototype is the C-type that represents a Lua function. So any kind of a source location is going to be a combination of a prototype representing some function and a bytecode number within that prototype. Whether this is the right prototype, we need to establish. We can see how the little dwarf thingy works here. We can go in, and expand things out. Just to like this. So we can expand things out. So this is actually a pointer in the C struct. It's a pointer to a GC proto object, and clicking this little toggle is basically dereferencing the pointer here in the UI. And not every pointer is dereferenceable, because when the virtual machine is logging memory, it cherry picks the stuff that it thinks is the most interesting. So if the virtual machine didn't think we were interested in this prototype object, then we wouldn't be able to expand that, because we wouldn't have the actual memory that it's referring to. But the VM happens to know that we're always interested in prototypes, so it always logs them. Anyway, so in there, in that prototype, we could scan through and figure out what what file name, what's the file name where the function was defined and so on. But let's just go a little bit more, because I'm not sure if that's the right prototype. We want the starting. Hey, this is interesting. Start PC, starting program counter. Okay, but that even that we don't have. That's interesting. So the starting first byte code address is not initialized. So this is backtracking for 1 second. What we're looking at here is, I'm going to hop over to the other view again. We have a successful JIT trace that compiled no bytecodes at all. And what this actually means is we had so many failures here. We had fail, 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 and then final failure, that we just said, bugger this. We're not gonna try to compile real machine code here. We're just gonna bail out to the interpreter. And so this successful compilation of 0 bytecodes is just successfully compiling a little bit of glue code that doesn't actually run any Lua code. It just bails to the interpreter. So, and the reason we don't get the starting line there is that it's just so empty. There's no bytecodes in the trace. So we're still just trying to find something that will be initialized there that'll tell us where the start was. And I guess if it's not there, it's not the end of the world. But we're gonna have a better look. So, have a program counter, although we really need to check whether that's valid, because okay, now we perhaps get to the interesting part. So this cur, this is the JIT trace that is being prepared. So if a compilation is successful, then this structJIT C trace is going to be the kind of ultimate result that represents all the machine code, intermediate code, bytecode, everything. And it gets kind of constructed gradually in place here. So this has a starting prototype, and it has a starting program counter. And that's actually probably enough to start instruction. So actually this looks like the right place to be looking. And there's a slightly tricky aspect here. So this is a structJIT C trace. We actually know how to decode that. We have a fairly elaborate Smalltalk representation of traces, but because this is a preliminary one that's still being generated from the JIT point of view, I'm not sure whether the VM is logging everything that we need. It would be nice to just take this, and it would be very nice to just take this and decode it into a full-scale object, and then it would use the code that we already have for finding the start location. But it's possible that the machine code, the intermediate code, and that kind of stuff will not have been logged. So let's see what we can. We take that object. Here is the GC trace. Zoom in on that. Oh. You can get the starting prototype. Should be able to also have a function for decoding. That's already decoded, so really all we need to do is this RaptorJIT prototype new from, if we say RaptorJIT prototype new from, would this work? No. what we're trying to do there is to take the C dwarf object and turn it into a higher level Smalltalk object. So, okay, so why didn't that work? Let's try that again from the debugger. It's because we're doing everything at the dwarf level, we're exposed to the C. We're exposed to the C type system, and here what we have is not a GC proto, we have a union. We need to just kind of like pick the type that we want there. So here, yeah, we have this union GC object. One of the views of this is as a GC proto there. So I guess that we could just kind of click on that. Now we're looking at an actual GC proto struct, so we're just mucking with the C type system at the moment. Okay, so then what about if we just said that? Okay. Now we've decoded the prototype successfully from a C memory image into a Smalltalk object here. It tells us immediately the source file name, so the only thing that we need after that is the line number. And I believe that we had something that we can use to get the line number. What was it? Start instruction 88, I think. I think that's what we need. Let's see what the GC proto. Prototype. Let's see what functions we've already written. Program counter. Okay, so we can give it a program counter and get a line number. Okay. Hang on. Is the program counter the most convenient? Anything else? Bytecode line. That's maybe better. We can give it a bytecode number and get a line number. So if the trace starts on instruction 88, then can we just ask the proto object which source code line was bytecode number 88 on? Worth a try, right? That's out of bounds. It did sound a bit high, so maybe I'm misinterpreting that. Maybe that start ins is not the bytecode number within the starting prototype. Seems like it should be, but a little bit of a browse around again. Let's try using the program counter. Start program counter. That's an actual memory reference. The first bytecode will be inside the prototype object. So we might just grab that number. Have to get back now. Object we had a moment ago was our just safe place. Then we grab our prototype there. Click that through until we get it as a GC proto. And there we'll do what we did before. We'll turn it into a high-level prototype object, and now instead of saying bytecode line, we will say a program counter line. a little bit. See, if we turn this small talk center. For funny reasons, I put that in square brackets. Nice. 9. Okay, so we did that the manual way, but it seems like this is a workable strategy. We want to know where a trace started, even if it didn't manage to trace any bytecodes. Then we find the cur, which is where the GC trace is being assembled. We find the start prototype, which is the bytecode function that we're in. And then we take the starting program counter address and we use that to look up into the start prototype there. So let's put all of this together now into this function we had here. So that's how this function is supposed to work. When we want to see the start source line for a JIT event, instead of doing this funny business with the number of bytecodes, we're going to first let's just what are we going to do? We're going to get a prototype, which we call PT because that's what the C code calls it, and a program counter. And we're going to say that prototype is JIT state cur dot PT, unless I'm misremembering. And so the program counter is JIT state dot PC. Hop over here briefly and see if that's right. Dot PT is right. Dot PC is right. With this dot PT, we're going to want to get that as a on here. So we need to say that. This is a little bit magical. So when there's a C object represented in Smalltalk as a raw C object, you can actually just send it a message asking for any attribute, and this will automatically get translated into a decoding step with the dwarf stuff. So I'm just freely using C identifiers here, and there's actually some code that I wrote that will catch those kind of unknown methods that don't exist, and just take the name and look that up with the dwarf info. It's a little bit magical. Then having those two things, we're going to say going to create a high-level representation of the prototype, and we're going to ask it for, what was the method called? Program counter line. Okay, so I'm sure that there's some bug there, but let's check that out. So now we have a new implementation that's loaded. We go back to our log. We get an error immediately. Okay, so when I'm saying cur, I'm wanting to send that to the dwarf, the low-level dwarf data, but I'm actually sending that to the high-level JIT state object. What is appropriate to do about that? We already have a method. We already have a method for getting the starting prototype, so let's see if that works. It might also be something that I was just writing while I was getting started on this. It may or may not be debugged, but let's see. see if that simpler version will work. And we have the same issue there, so maybe this is actually the place to do it. Maybe this JIT state object should have the function that gets the starting source line. Let's do that. We have start prototype. Let's say start source line will be right up, and this would just be to get the if it works, we will explain what we did. Well, pick this somehow, let's refresh. Okay, obviously there's something wrong with the start source line. Oh, sorry, that's wrong. Not prototypes. Source line. Again. I print the stop event. We want to get the start source line. We're getting a number back for the start source line instead of a string. That will be because of something that we need here. Ah, okay, of course. Any number because we're just getting the line number. What we want source line. So we need to convert. We need to say line. Line is that. How do we usually format? Source. Okay, I think that we want to do this. We want to say then I want to return the prototype source name followed by a colon followed by the line string. I think that can possibly work. There we go. Yes, I can return that. Some programming languages want you to put in return statements, like Smalltalk and Lua. Others don't. I guess it's fixed away. Again. Ah! It worked. This is the line. Okay, that's our first to-do is actually working now. This one before said trace stop success from question mark we don't know because there were 0 bytecodes, and whereas now it's getting the actual beginning position. So that's actually very nice first step. So that was the simple bit, and I started a bit late, so it's nearly lunchtime. So I will actually probably quit while I'm ahead now and continue with the other stuff another time. This is nice. So now what we've just done is to go deep into the kind of the bowels of the virtual machine's internal representation of the JIT state while it's attempting to compile something. And we found a more reliable way to see where did that JIT compilation attempt start. So now we have a way to see where the JIT event started, even if it compiled no bytecodes, without referring to the bytecodes, which is nice. So I'm actually going to check this in and push this because Raj, the snap hacker, is actually waiting on this to debug a performance problem. So I will sign off now. I'm going to push this to a branch where he can pull that, and then the next thing I'm going to do is this other step. Going back over to our goals. I'll set the new goal now. Is going to be to go backwards from pulling it up again. Next thing that we want to do is to be able to go backwards, where we go through the profiler data, we go clickety-click, find trace somewhere, and we want to be able to go backwards and say, sorry, here, we want to go backwards and say where, what were the JIT events that led to this trace running into the interpreter. That's for next time. Cool, nice. Thanks for following along. This was fun. Bye-bye.